So yesterday we understood the concept of slicing, basic concepts of slicing, how the slicing is basically done, what is adaptive slicing and what is uniform slicing. So today I will just explain to you some of the algorithms that were developed through the course of time, which were incorporated in various softwares which are utilized for slicing. The first concept that was presented ever was given by Dolinek and Makla in 1994, and it was called as the cusp height tolerance concept. So I hope you remember what is a cusp height, because that concept is now going to be utilized in subsequent algorithms also. So just to give you a brief idea what is a cusp height. So if suppose these are the two layers, so if I create a facet with the overhang, this is the overhang and this is layer thickness, then this triangle is called as the facet, and the vertical distance between the joining of the overhang and layer thickness and the other edge of the facet is called as the cusp height. This is called as the cusp height. So Dolinek and Makla actually gave a concept where the cusp height was utilized as the basis of evaluation for the optimal layer thickness basically. And what he basically said that if you have any if you have any figure or if you have any profile, then in that profile basically there will be lots and lots of facets which are going to be created at the edges. So now cusp height is going to be denoted as C. So what he said was that every triangle, every facet will have a unique cusp height. So suppose if there are if there is a figure like this, so there are going to be three triangles, and each triangle will have its own cusp height. So C1, C2, C3, and each cusp height each value will be unique. So it means that if there are n number of triangles which are generated during the slicing process, so there are going to be n cusp heights. Out of those n cusp heights, you have to find the value of the maximum C. Which of these three, assuming this example, which of these three will have the maximum value? So let us assume C3 is maximum. Then what he said was, this is going to be the maximum surface roughness that is going to be generated. So this is going to be the maximum surface roughness that is going to be generated. Hence, the layering process will be done according to the maximum surface roughness that is going to be created due to the maximum cusp height. Another thing that you already know is that each facet will have a unique surface normal. Each facet will have a unique surface normal. Okay. There will be unique surface normal for C1. There will be a surface normal C2 and C3. For every triangle, there will be a surface normal. So corresponding to the maximum cusp height, what is the value of the surface normal? So that is assumed as this. Every surface normal has a characteristic of nx, ny, and nz. Every surface normal will have this characteristic. So now you have a triangle, and you have a surface normal. And also what you know is what is the maximum cusp height. So what he said was the layer thickness will be equal to the maximum cusp height divided by the z vector of the surface normal. So every layer thickness will be defined, or the uniform layer thickness will be defined as C max divided by NZ, where T is going to lie between minimum and maximum thickness that can be assumed. Now, what the maximum thickness can be assumed is if NZ becomes equal to 1, then T equal to T max. And when NZ equal to maximum, like if it becomes say 10, then T is equal to T minimum. So this is how maximum and minimum was assumed. Generally, the value of nz is in the range of 1 to 10. Generally, it is in the range of 1 to 10. So this is the value that was assumed for layer thickness. So every layer thickness is equal to the maximum cusp height derived by the triangles divided by the z vector of the surface normal of the same triangle. So this is how he defined, or how he assumed, the surface roughness to be found out. This process was actually developed not by some means, but it was an accidental discovery. What happened was, when Dolinek and Makla actually used this concept, and this concept was implemented into softwares, only uniform slicing was possible. Only uniform slicing was possible. Now, you didn't still had the flexibility of going into adaptive slicing. So what Soborin did was, he used adaptive slicing using stepwise uniform refinement. So how did he find the uniform refinement? Initially, what he did was, he found out the maximum value of C. He found out the maximum value of C for the figure that they were trying to direct. So C basically gave them the cusp height. C basically gave them the cusp height. Now, based on that cusp height, or C maximum, basically, based on this C maximum, they identified what will be the maximum layer thickness. What will be the maximum layer thickness? Now, once they identified the maximum layer thickness, the whole object was now divided using Tmax. The whole object was now divided by Tmax. Then for every layer, the condition that C equal to C max was actually evaluated for every slab. Now, if this is slab 1, this is slab 2. So like this, for every slab, they evaluated the basic condition that C equal to C max. Now, wherever this condition or this condition was not satisfied, wherever these conditions were not satisfied, that slab was identified. Now let us assume slab 2 did not satisfy this condition. So what they did was, they simply took slab 2 and used the criteria again to divide it into finer slabs. So in order to reduce the cusp height, of this slab, what they did was, they further refined it into smaller layer thicknesses. They further divided it into smaller layer thicknesses. So now what happened was, the surface actually had a sort of adaptive slicing concept, where the first slab was bigger, then there was finer slices, and then again there was a larger layer thickness. So wherever this condition was assumed and it was satisfied, this concept was taken. So I'll just explain it again. So initially they took Tmax as taken by Dolinek and Makla. Once the Tmax was identified, Cmax was also identified. Taking Cmax as the value, they found out the value of cusp height for each of the slabs. And wherever this cusp height was not satisfying this criteria, or this criteria, C equal to Cmax, or C should be less than Cmax. So wherever this criteria was not satisfied, that slab was identified. And then that slab was divided into finer slabs so as to reduce the value of cusp height and to bring it under these constraints. Now, this was very easy to implement when you had a simple figure, but when you had large number of slices, evaluating each and every slice became slightly difficult. So they came up with an empirical formula. So what was the empirical formula? What they initially wanted to find out was the alpha of the slab. This was a number. This is basically a number which they wanted to determine in order to understand what will be the value with which the layer thickness can be defined, which will actually satisfy this condition. So what they did was they took alpha slab, that is an integer, that's an integer number, because what happens is sometimes if you divide the number it comes out to be 3.75. So getting 3.75 slabs is not going to be possible. So this is the number of slabs that you are trying to get. Okay, so if by default if you put this equation into consideration, it is that like your T max would come out to be like 375, and T min, if it comes out to be 100, this becomes 3.75. So you cannot have 3.75 layers. It can be either 3 layers or it can be 4 layers. So for that they defined it as an integer. So integer means even if it is 3.01, you go to the higher number 4. Even if it is 3.01, you go to the higher number 4. So that is why this integer was introduced into the system. So they took as integer of T max divided by C max. And then what they said was that for every surface that is going to be created, there are going to be two surfaces. What are those two surfaces? There is going to be an up surface and there is going to be a down surface. Up surface means when you move up the surface, and down surface means when you move down the surface. So for every profile, because these two profiles will be identical. So what they wanted was they wanted to find out this NZ value. This is called as the up surface and this is called as the down surface. So they wanted to find out for the up surface and down surface what was the NZ on the top and NZ at the bottom surface. Now once they found out NZ and for both the surfaces, which of these two has maximum value? So which of these two has maximum value was selected, and that was multiplied with this factor. It was multiplied with this factor. So they further simplified this formula. As simply alpha slab is equal to integer of T max by T min. So T max and T min you can easily find out using Dolinek and Maclau's concept. So T max and T min you can easily find out using Dolinek and Maclau's concept. So using that concept, when you find T max and T min and you find an integer, you find the number of slabs. Like if you have a maximum layer thickness of 500 micron and a minimum layer thickness of 50 micron, so the alpha value will actually come out to be 10. So you can have 10 slabs. Now, once you have 10 slabs, what will be the layer thickness? So the maximum layer thickness divided by 10. So maximum layer thickness was 500. That is divided by 10. That will give you 50 micron. So if you go by this layer thickness, what you will obtain is the value of C max will be less than C max always. So indirectly what Soburin actually told us was that it is always better to create a part where the minimum layer thickness is considered. So this actually gave a very good surface finish. This concept actually generated very good surface finish, but the problem of build time started to creep in. Because since you are making with the smallest layer thickness, so the number of layers are going to increase, and as a result what will happen is your build time is bound to increase. So this whole concept actually worked very good with respect to layer thickness, but build time was compromised in this concept. Then another method came which was introduced by Tyberg, and then again he worked in conjunction with Born, and they came up with a local adaptive slicing of parts. Now local adaptive slicing also used the basic concept of Dolinek and Maclau, that is the limited Cuspite concept. However, they had a slightly different take than Soburin. So what they did was, I'll explain this with an example. What they did was they took this object as a steady. Now if you can see this object, there are wide variety of surface areas, like this one is inclined, this one is vertical, this has some inclination, and then varying varying section thickness. The section thickness varies. So when you have got different parts, it is not advisable to go for a uniform concept. It is not advisable to go by uniform concept. So what they did was, initially they took all the regions as a single region and divided the whole body into uniform parts. So what they did was, in all the individual parts were identified, and the features in the build were identified and slicing carried out independent of one another. Now there are three basic features. This is one feature, this is one feature, this is another feature, and then after this section, this is another feature. So first of all, you have to identify what are the critical features. What are the critical features in your object? Now, once you identify those critical features, once you have identified those critical features, then you have to identify how the slicing algorithm is going to be implemented. So you also have to decide on the slicing algorithm. So first, if you have this as 1, 2, 3, and 4, so let us take 1. So for 1, an independent slicing algorithm was defined. The slicing algorithm actually was based on Dolinek and Makla. The slicing algorithm was based on this concept also, only limiting cusp height, and this had a different layer thicknesses. Then they went to the second. Second had a uniform cross section up to here, and then a slightly varying cross section. So again, using the concept of Dolinek and Makla, this was layered off separately, this was layered off separately, and this was layered off separately. So once each slab has been identified, now then you went into the second concept that you have just seen, that is of Soburin. And what you did was, each layer now was defined on the basis of how many slabs are actually needed to create the part. Like for this part, you had finer layer thicknesses, whereas for this part, you can have thicker layer thickness. So depending upon the cross section of that individual part, so a single object can have local adaptive slicing as compared to uniform adaptive slicing. So every feature, every portion, every significant region of your model can be sliced separately. The advantage was definitely that the build time was saved significantly. The build time was significantly saved because rather than having a uniform adaptive slicing or uniform slicing, it had local adaptive slicing. So every layer, every feature, every component had its own critical features. But the problem came out in a different way was with regarding the geometrical efficiency or geometrical deviations. Since some parts had thinner layers and some parts have thicker layers in the same model, so geometrical inaccuracy started creeping in at different sections, which was very difficult to control, because thinner layers actually create better geometrical accuracy. Thicker layers have more contraction. As a result, the geometrical accuracy is compromised. So definitely the build time was saved using local adaptive slicing, but the problem of geometrical intolerance or geometrical inaccuracy actually started creeping in. As a result, this concept was, although very effective in most of the cases, still it did not solve the problem of mechanical inaccuracies. Then Soburin came up with another model in 1997, and this model was actually not based on geometrical tolerance, but it was based on more saving the build time. So he basically gave this idea of saving build time. Now what he said was, Using his earlier concept, what he said was that for every model that is going to be developed, there are two zones which are of importance. There is an inner zone, and there is an outer zone. Okay. So inner zone basically contains the core. Of the CAD model, and outer zone basically contains the features and the surface accuracy concept of the model. So what he said was, rather than having different slices at different cross sections, what we can do is we can basically break this whole model into initially two sections, that is inner and outer. So inner zone basically requires more strength as compared to the outer zone. So the layer thickness of the inner zone can be higher. As compared to the outer zone. So layer thickness is lower. So he divided the whole section into two parts, that is inner and outer, and inner zone can have higher layer thickness and outer zone can have lesser layer thickness. Now, once you have identified inner and outer zone, what you simply do is it's a basically union now. It's a union of two solids. One solid has got features, the other solid has got rigidity. And you union those two solids together, you get inner and outer. I hope you understand what I'm saying. So the outer zone is sliced differently and the inner zone is sliced differently, and then they are joined together and a solid is going to be created. Advantage, definitely, as I said, the whole advantage is of build time, which can be reduced up to 50 to 80%, because here also you can see there are three layers and there is a single layer. So create a lot of time is definitely going to be saved when you create with a higher layer thickness. And since it is on the inside, the layer thickness, although it is higher, will give you better strength as compared to small layer thicknesses, because adhesiveness or joining becomes a issue most of the times when we have thin layers. So you get better time saving, and this process was actually called accurate exterior and fast interior. So this concept was called as accurate exterior and fast interior. Then another concept came from Tata. Now this concept was actually based on STL file. And I need to go back to just explain the STL file once again. What you are talking about is basically the idea that STL file is not only having information, it is also a key characteristic identifier which can be used for generating slices. So Tata actually developed an algorithm using MATLAB, and his algorithm basically contained four important components. First was the Facet Processor. So in Facet Processor, basically all the triangular facets which were there in an STL file were compressed into groups, which were based on their location with respect to the base of the model. Like if you have this cube as a model, so the whole surfaces were divided into facets. You know how the facets are generated now. So whole information is now divided into facets, and based on the base, where the base is, the location and the vertices were actually identified, and then they were grouped together. The arrangement was actually an unordered structure, because every relative position with respect to was actually stored in a form, but unordered collection was done. So in order to remove that unordered collection, what happened was sorting of coordinate of vertices was done. In order to create a structured collection, what they did was they performed sorting of the vertices. so that the z-axis of each vertex was evaluated, and based on that, facets were arranged in such a way that you could generate the exact feature during reconstruction. You could generate each feature during reconstruction. So that is how facet processing was done. Then the second part of their algorithm was identifying the key characteristic. So here what they did was they used a simple geometric and engineering principle, that is, which is to find which are the horizontal surfaces which have pointed edges and which have pointed ends. Okay. So once they identified these, they were also able to identify the type of features that this model had. Like if there is any protrusion or if there is any depression, like if there is something like this is called as protrusion, and or something like this, which is called as depression. So every geometrical shape and feature was identified, and once geometrical shapes and features were identified, and based on their surface normal characteristic, their orientations were also identified. So basically what you were trying to do is, like if I create a dotted structure over here, so this is your base CAD model and this is your protrusion. So this is also divided into number of triangles. Each triangle has their own surface normal. Based on the direction of the surface normal, their geometric features were identified. It was identified by the surface normal. If the surface normal is pointing outwards, then it's a protrusion. And if it is pointing inwards, then it is a depression. So based on these characteristic features, you were able to identify what were the main characteristics of that CAD model. So first you recreated the CAD model with the help of STL file, that is the triangular facets, and then using the characteristics of each and every facet, that is the horizontal surface, edge, surface normal, orientation, you were able to identify if it had any specific characteristics. Now, once you have identified the characteristics, now you started to define the layer thickness. So the layer thickness is basically based on the geometrical complexity of the surfaces that are there on the part. And the complexity is defined as S equal to tan theta, where theta is the acute angle between the slice axis and the projection on the surface. So what happened was, like if you had a surface like this and you divided it into, let's say, 4 basic triangles, now there's a surface normal, and the surface normal will definitely create an angle theta. The surface normal will definitely create an angle theta with respect to the base. With respect to the base, it will create an angle theta. Now, what we had to first of all find out was where this theta is acute angle. Where this theta is acute angle. So that orientation was taken to be the ideal orientation. So where theta is acute, that is taken as ideal orientation. And once the projection, that is the surface normal, is identified and theta has been identified, simply you defined S equal to tan theta, you found out the value of S, and based on the minimum value, because acute angle is from 0 to 45 degrees, 0 to 60 degrees. So if theta is 45 and if theta is 47, the value of S changes. The value of S changes basically. So wherever you got the minimum value of S, that is the surface projection, so you took that value, and with zero complexity surface, wherever the zero complexity surface was obtained, that layer thickness was assumed to be the layer thickness. That is the maximum allowable layer thickness. And based on that, the layer thickness was defined. So what we were trying to assume is zero complexity surface. So wherever the surface this complexity value S started to go as minimum as possible, that value was picked up. Zero complexity surface is theoretical concept. It is not possible in any STL file. You cannot get a zero complexity surface, but the minimum value of S can be definitely found out. And using that minimum value, the layer thickness is defined. For complex surfaces, basically it is t into tan theta, and the chord length is t equal to cos theta. So the basically this whole concept becomes, the criteria for maximum deviation becomes cos theta into tan theta, and it becomes slightly difficult to comprehend over here. This becomes cos theta into tan theta. So find, if you obtain the value of theta and multiply that by cos into tan, you would end up having equal it to sin theta. So maximum deviation criteria was useful only when you had a simpler surface where you didn't had lot of complexities. Now complexities basically means like if there is a surface like this, now here you have got lots of protrusions and lot of curvatures, and creating the obtaining S for this type of a surface is very difficult. So for simpler surfaces, this algorithm actually worked very nicely. But the problem with this algorithm is, when you have got a complex surface, finding out the layer thickness and the maximum deviation criteria is somewhat difficult, because generally what happens is, what researchers have seen and what people have told is, you get multiple options. You start to get multiple options. And due to multiple options, it becomes very difficult to identify which is the optimal answer. Hence, for simple surfaces, the minimum value of S is there, and you can use that minimum value of S to define the minimum layer thickness. But for a complex surface where you start to get multiple answers and multiple orientations, in that case, it becomes very difficult to select the optimal orientation. The last stage of this algorithm is the slicing. So once the two-dimensional contours are created, you simply take the layer thickness that you have assumed, that you have found out, and you use that layer thickness to create the part. Now, another concept was taken into consideration, that is the volumetric error. Another concept was also incorporated later on, where you had a volumetric error concept. Now in volumetric error, what happens is that this is a cube. This is a cube. It has got a volume. So what will be the volume? L into B into H. So this is the volume. Now, once you have sliced this, once you have sliced it, definitely there is going to be some loss of information. Some loss of information. Now, if you recreate this STL file, there is a very good chance that the volume may be actually L dash into B dash into H dash. That is layer thickness, cross-sectional area is B into H, layer thickness, cross-sectional area, any of these factors may get compromised due to the slicing process. Therefore, what was assumed was the volumetric error per unit length was maintained as constant. So volumetric error per unit length was assumed to be constant. So that also criteria helped somewhat, but it only again helped only for smooth surfaces or easier surfaces. For difficult surfaces, it was again not possible to do that. Then what happened was, all these algorithms that you have just seen are actually based on maximum allowable cusp height. And in order to understand maximum allowable cusp height concept, you have to understand that all the edges are assumed to be rectangular. The edges are actually assumed to be rectangular. Due to that, the maximum allowable cusp height was generally C1 was equal to C2 was equal to C3 is equal to C max. Means most of the cases, the cusp heights that were found out generally had an equal value, same value. But if you have something like this, a parts like this, in this case, if you start creating slices, what you would obtain is different set of triangles. Now, when you get different set of triangles as compared to here, Like if you compare these two triangles, what you would find is C1 is not equal to C3. So a concept of non-uniform cusp height was brought by Cormier in 2000. And another thing that he found out was the edges. Another thing that he considered was edges. Most of the cases, the edges, as I explained, was considered to be rectangular. But for non-uniform cusp heights, the edges were actually considered to be, or actually found out to be, parabolic in nature. They were actually found out to be parabolic in nature.